Welcome back. We're going to continue with our second unit in Chapter 5, Section 5-6. The goals for this lesson will be the following. List the possible rational zeros of a polynomial function and use the list in the graph of the function to find all real solutions to a polynomial function. So those are going to be our two goals for today. Make sure you have it here at the top of the notes. So I know you copied the correct ones there. So finding rational zeros using the rational zero theorem. That's how we're going to find rational zeros. It's this theorem. It says if f of x equals a sub n of x to the n power plus dot dot dot, and that dot 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 means the pattern continues in such a way, plus a sub 1 times x plus a sub 0 has integer coefficients. Integers, what are integers? Okay, integers means no decimals. -3, -2, -1, 0, 1, 2, 3. So the pattern continues on either side. Okay, positive or negative counting numbers to 0. And every rational zero of f has the following form: p over q, where p is factors of the constant term a sub 0, and q are the factors of the leading coefficient. So that factors are numbers that divide a number. So numbers that divide the constant term, the last term, and numbers that divide the leading coefficient. The first coefficient in standard form. We backtrack here. Rational zero. I just realized that rational numbers are numbers that can be written as a over b, where a and b are integers. So basically fractions. Okay? Any number that can be written as a fraction is a rational number. Those could be repeating decimals. They could be decimals that are finite. Irrational numbers are numbers like the square root of 2. It has no repeating decimal, cannot be written as a fraction. Okay, so just a couple things to point out as we go through when you're reading this. So what does that all mean? It means we can list out possible rational zeros by just looking at the equation. So first of all, we look at it. In order to use the rational zero theorem, you have to look at the polynomial. You have to say, okay, does it have integer coefficients? 3, 2, -3, and 6, those are rational numbers. I don't see integers are rationals, but integer values. So we need no fractions, no decimals. So I can use the rational zero theorem. So how do we do that? Well, first we have to identify what is p over q. P over q, in this case, is, well, P, it said, refers to factors of the constant term. Our constant is whatever the last term is without a variable by it. So 6 is our a sub o. And our q is the leading coefficient factors. So we're going to get the q values from 3 in this case, the leading coefficients. So what are numbers that divide our a sub 0? What is our possible p values? Well, possible p values are no factors of 6. So what divides 6? 1 obviously does. 2 divides 6. And 3 divides 6. And of course 6 divides itself. So those are all possible p values. Q comes from the factors of 3. So 1 or 3. Notice I put plus or minus because you could have a positive or a negative number divide 6 or 3. So that's not how we write our answer, though. We list them out. So we're going to go through and basically we're going to divide this up. The top numbers get divided by each of the numbers in the denominator. So 1 divided by 1 is 1, plus or minus, right? Because it's positive or negative. 2 divided by 1 is plus or minus 2. 3 divided by 1 is plus or minus 3. And 6 divided by 1 is plus or minus 6. Now we have to do the same thing, except this time we're going to divide by this 3 on the bottom. 1 divided by 3, plus or minus 1/3. 2 divided by 3, plus or minus 2/3. 3 divided by 3 is 1. I don't have to write 1 because I already have it over here. So I don't need to write it again. And then 6 divided by 3 is 2. I already have 2. I don't have to write it again. So this would be a list of all the possible rational zeros. Does this mean that every one of these values is a 0? That's false. That is not true. In fact, you may not have any of them that are zeros. If all your zeros are irrational numbers, or if you have imaginary zeros, none of these could possibly be a solution. But these are possible solutions, and I'll show you how we're going to use that in a minute. If you really want to see which ones work, you can plug them in one at a time, back into the function, and see which of them with them give an output of 0. Okay? I'm going to show you a different way to do it, but that is one possibility. So that is finding the rational zeros, listing the possible rational zeros. Here are some examples that you can try. I'm just going to give you the answers to them, and I'll leave you to attempt the problems. So that's what the rational zeros you should get from this example. And for this example, these are the following rational zeros that you should end up with. Remember, we don't have to write repeated zeros or possible zeros. So if an answer repeats, if it's a fraction that reduces to another fraction, hint, hint, we don't have to write it more than once. Okay, so try those problems, those are the answers, see if you can find all those zeros as you go through the problems. So, finding all the real zeros. Here are the steps to finding all the real zeros. I would expect that you put these in your notes so you have them for later. Make a list of all the possible zeros. So we're going to go through with the rational zero theorem. We're going to list out all possible zeros, in this case rational zeros. This is a real zeros, but we'll see how that make that connection as we go through the section here. Use a graphing calculator to find 1, 0, the x-intercept. Now, I would graph it, and we'll show you how to graph it, or you could do, like I said previously, plug them in one at a time until you find an output of 0. Then you're going to use synthetic division to factor. And you might have to use the calculator twice to find the x-intercepts. And set factors equal to 0 to find solutions, zeros, roots, x-intercepts. So we're going to go through, we're going to apply those steps. So if you pause it to get the rest of these down real quick, and then I'm going to slide the problem down here so I have some room to write. So here's our first problem. F of k equals k to the third minus 4k squared minus 15k plus 18. So make a list of all of zeros. That's the first step. So we're going to use the rational zero theorem. P divided by Q. Okay? Well, P comes from the constant. We're going to get a constant from P, and Q comes from the coefficient of the leading term, or the first term, leading coefficient. I'm trying to say here. So P, 18. What numbers divide 18? Well, you could sit and think about it for a minute. But 1 and 2 divide 18. 3 and 6 divide 18. 9 divides 18. And 18 divides itself. And we always put plus or minus because it could be positive or negative values. Q is 1. Whenever Q is 1, we should be very happy because basically that means that P divided by Q is simply the factors of P. So 1, 2, 3, 6, 9, and 18. Those are our possible rational zeros. Those are not the answers. This is where students stop. If I ask you on a quiz or a test to list the possible rational zeros, you would stop here. If I ask you to find the real zeros or find the zeros, you would keep going. So the next step, it said, use the graphing calculator to find at least 1 0. So we're going to go pick up our graphing calculator. We're going to go to y equals, and we are going to put in our equation. Instead of k, I'm going to use x. I hope that doesn't upset anybody, but oops, our calculators really don't let us use k. We have to use x all the time. I'm sorry about that. I did not design it. So if you have a problem with the way it's designed, you might want to contact Texas Instruments. But until then, we just have to use x every time. I'll put 0 in for y2. That'll help you find where it intersects the x-axis. I go to graph. Remember where it intersects the x-axis, those are our zeros. And we might be able to find all of them on this graph. In fact, it looks like we can find all of them. Looks like they're all integer values. Okay, but we're going to pretend we can only find one of them. Okay. Well, we won't pretend. We'll find all of them, I guess. But then I'm going to go back and we're going to pretend. I'll show you what you would do if you can't find all of them. So if I look, it looks like at 1 and 0, that's a 0. So 1, 0, that makes 1 is 0. Negative 3 has an output of 0. That makes negative 3 is 0. And then if we go up, that's not going to work. So if we look at our graph here, I'm going to cheat, look at my graph on the other window down there lower, and I can see if we can get down here to about 5 or 6. Looks like 6. So negative 3, 1, and 0 appear to be intersection points. Those appear to be our zeros. How do we know that they are for sure? Well, we are going to use synthetic division to factor. Now, could you use long division? Yeah, we talked about this last time, but we're not going to. I'm not going to use synthetic division because I think, or excuse me, long division because I think synthetic division is faster. So here's our polynomial: k cubed minus 4k squared minus 15k plus 18. I don't have to put in any zeros. I'm just going to put in the coefficients: 1, negative 4, negative 15, and 18. Pick your zero that you want to work with. Oops. Negative 3, 1, and not 0. 6. I think I said 6, but I wrote 0 there. We're going to pick one. Doesn't matter which one. I'm going to pick negative 3 just to prove that it's a 0. Negative 3, or excuse me, bring the 1 down. 1 times negative 3 is negative 3. Negative 4, negative 3 is negative 7. Negative 7 times negative 3 is 21. 21 plus negative 15 is 6. 6 times negative 3 is negative 18. And that 0, that's our remainder. That's good. If you get a remainder of 0, that proves that negative 3 is a 0. So, how does that work? Well, that tells us that if negative 3 is a 0, then x plus 3 is a factor. Okay? And so we have 1x squared minus 7x plus 6 as another factor. Okay, now we already have the zeros. We have 1 and 6, but not always does it work out that way. So you may at this point be able to factor this polynomial, this quadratic left. If you can't factor it, then maybe you complete the square to find the zeros, or you use a quadratic formula. Let's see if we can factor this one using bottoms up. Just to show you what you might do if you can't find all the zeros. Factor, quadratic formula, completing the square. Those are other methods we have. Because if we have imaginary zeros, we can't find them by graphing. So, A times C, 1 times 6, what adds to make negative 7? Deposit, try your own. If not, negative 1 times negative 6 is positive 6. Negative 1 plus negative 6 is negative 7. So we get x plus 3 is already a factor, x minus 1, and x minus 6. Because a up here in front of the x squared, because that is a 1, when a is 1, you don't need to go through and do the dividing by a part. But if a was not 1, if a was something else, we would obviously divide by a. We have factored it. It did not ask us to factor, it asked to find the zeros. So what you do then is you set each of these factors equal to 0 and you solve. And we're going to see that by factoring we get the same 3 answers that we found on our graphing calculator. Now, I'm showing you this way. You're saying, well, Mr. Kuhn, why did we go through all this? It was silly. Why did we do that? Because not all of them will factor out like that, or not all of them will have, the zeros listed in the from rational zero theorem be the actual zeros. You may have irrational zeros. You may have fractions that are harder to see on the graph. You may have imaginary zeros that you can't see on the graph. So that's why we need to be able to use the concept of synthetic division or long division to factor it out and then get it down to a quadratic that we can either factor, complete the square, or use the quadratic formula. So let's see if we hit all those targets. Did we hit our targets today? Yes, I think we covered listing all the possible rational zeros of the polynomial function, and I think we covered graphing or using the list and a graph of a function to find the real solutions to a polynomial function. So have the notes ready in class for tomorrow, and we will practice more of this all together. Have a good day.